Hello all, myself Mahendra from Robotics and Mobility Systems, along with my teammate Ashutosh Sahu, will be presenting our work on the topic semantic segmentation as a part of our course project in the subject computer vision. Semantic segmentation is a powerful technique that goes beyond the object detection and classification, aiming to understand the images at a pixel level. It involves assigning the meaningful label to each pixel in an image, thereby enabling machines to comprehend and interpret visual scenes with a remarkable precision. This breakthrough technology has revolutionized various fields, including autonomous driving, medical imaging, video surveillance, augmented reality, and more. The simple understanding of semantic segmentation is that we try to separate a foreground and background from the image. For example, in the below image, we can see that there is a person standing in the image, and we have tried to separate the foreground, that is the person, and the background, that are some other features from the image. There are classical and modern approaches for the semantic segmentation problem. Classical approaches refers to SVM, random forests, mean shift, etc. The modern approaches refer to the approaches using CNN models such as YOLO, SegNet, VGGNet, ImageNet, and U-net, and some more. In the subsequent slides, we have demonstrated results from each of the methods that we have implemented. Now I hand over this to my colleague Ashutosh Sahu for further presentation.
Thank you, Mahendra. I am Ashutosh Sahu. Now I will further explain about our project. Starting from classical approach, the first model we have used is the random forest model. Random forest is an ensemble learning algorithm that combines multiple decision trees to make predictions. Each tree is trained on a random subset of the training data and a random subset of the features. The final prediction is determined by aggregating the predictions of all individual trees. Random forest offers several advantages, including robustness against overfitting, scalability to large datasets, and interpretability of the learned model. We have used random forest on aerial image dataset, which basically contains images of the ground taken through a drone. These are the results that we got from our model. Here you can see that the second image is the segmented image of the first image. And on the right side, we have the ground truth segmentation. As you can see that the model was good enough to segment the given image. The ground truth segmentation contains pixels with their corresponding labels. These are labeled manually through online resources. The accuracy of the random forest model on this dataset was about 80.68%. Here the accuracy is low, which is because we have used handcrafted features. Random forests face challenges in handling fine-grained details and capturing complex spatial relationships. Additionally, the computational complexity can be higher compared to other deep learning-based approaches, which we are going to explain in our presentation. Now let me explain about the code. Here is the code for our model. Now, in our code, we have extracted a new set of features which are known as Gabor features. Gabor features are extracted using Gabor filter. This filter is a linear filter which is used for texture analysis. It looks for a specific frequency content in the image in specific directions in a localized region. Here we have used about 32 Gabor features for one single image. We have also extracted some other features using Canny Edge, Robert filter, and Sobel filter. Then we have created a data frame which will represent all those features. After extracting these features, we have used the random forest model from the sklearn model. The random forest model was used with 20 estimators, which means we have used 20 decision trees. The accuracy we got is about 80.68%. Here, these are the list of the features as per their importance. Here we can see that the Gaussian filter with these sigmoid equals to 7 has a higher weightage than other features that we have used. The final segmented image is shown. Below on the left, we can see the model segmentation, and on the right, we can see the ground truth. Now, my friend Mahendra will explain about the SVM model that we have used.
Now I will explain about the SVM model that we have. SVM, short form for support vector machine, is one of the most popular supervised machine learning algorithms that is used as a classifier and in regression tasks as well. There can be linear or nonlinear SVM based on the hyperplane that we need. The hyperplane is nothing but a plane that cuts through the dataset and separates the dataset into separate groups or classifies the dataset. In our implementation, we have used the linear SVM. SVM defines a hyperplane in n-1 dimension where n is the number of data dimensions. The SVM tries to maximize the margin to overcome the misclassifications that can be happening with the dataset. Now let me just demonstrate the code snippets for the support vector machine. Here we have used the same set of the filters that we have used in the random forest, and we have extracted the same set of filters such as Gabor filter, robot filter, etc. Now, if, as we can see here, these are the same set of filters. Now, the SVM models performs poorly in this dataset because SVM is a classifier which needs a distinctive boundary between the two datasets. Now, here we can see that SVM we have used maximum iteration of 100, and there was a due to the hardware restrictions we are only able to iterate it up to 100, whereas we can also go for 1000 for the higher accuracy. Here we can see that we have only achieved accuracy of 33% because there are the images that we get from the ground truth segmentation have the overlapped features. Here we can see that the result from the SVM model. The left side image gives us the model segmentation and right side image gives us the ground truth segmentation. As per the accuracy, we have expected this kind of results from the SVM model only. Now we'll dive into the modern approaches using the convolution neural networks. We can segment the images from the convolution neural networks very efficiently than the SVM and the random forest models. The first model that we tried was YOLO, which stands for You Only Look Once, which is a popular real-time object detection algorithm that has gained significant attention in the field of computer vision. It stands for its ability to achieve fast and accurate object detections in images and as well as videos. The key idea behind the YOLO is to treat object detection as a regression problem, where the algorithm directly predicts the bounding boxes and class probabilities for multiple objects within an image in a single pass. Unlike other object detection algorithms that use a sliding window or regional proposal based approaches, YOLO divides the input image into a grid and makes the prediction based on that grid. YOLO needs to have an pixel augmented data where we need to give the manual labels to each and every individual pixel, which is a tedious task. We have used YOLO V8 on the COCO 128 dataset. This COCO 128 dataset contains 128 images of RGB channel, and the dataset consists of 80 labels including person, car, aeroplane, bottles, etc. We have tested models by our own images taken inside and outside our IITJ campus. The original paper on YOLO architecture was presented in the CVPR 2016 edition, and it won the People's Choice Award in the CVPR. The architecture can be seen below. It consists of several convolution neural network layer and dense layer at the end. In this approach, we have used YOLO version 8. This version was developed by a company called Atalytics, and we have used their documentation in order to develop the Python code for this particular problem. Now let me take you through the code snippet for the YOLO V8 architecture. Here we can see that we have just installed the Alterytics module from the people with the help of pip, and we have loaded a YOLO module. We have loaded a model which is YOLO 8n segment.yml. This YOLO 8n is nothing but YOLO version 8, and N stands for nano. There are several models starting from nano, small, and goes up to X, which is large. The segmentation model is then loaded and trained with the COCO data. and we have used the epochs of 100 for getting a higher accuracy. Now, if you can see, we have trained the images, trained the Coco dataset, and we have run our own datasets for the uh, run our own dataset for the testing purposes. Now, let me just show you some of the results that we got from the uh, YOLO V8. Here is the some web image that I took. Here we can see that the truck cars have been detected, but they are not perfect. We can see that the confidence level of the car can vary from the range of zero point 0.5 to as high as zero point 0.9. Here we can see a person being detected. The confidence level is about 86%. Here this is the our group where we can see that we have taken an image in a group, and it is the YOLO was able to predict most of the persons in the image, but we are not, there are still some errors in the detection. This is go for the same. Here we can see that there are some detections from the cup and bowl in the dining table. So now let me explain some of the matrices that we used for the evaluating the performance of the YOLO architecture. We can see that we have a covariance matrix, we have matrix from mean average precision, and there is a training loss. The mean average precision, we can see that there are two types of mean average precision, that is B and M. B is for the bounding box, M is for the masked dataset. The covariance matrix contains 80 about 80 classes that it needs to predict, so it is very big matrix. So we cannot see all the dataset all the data in this particular slide, but we have attached in the report as well. Most of the CNN can be evaluated with some of the matrices such as intersection over union or IOU index. It measures the overlap between the predicted bounding box or segmented region and the ground truth. IOU is calculated as the area of intersection divided by the area of union between the predicted and the ground truth regions. Average precision. In context of object detection, average precision is often used to evaluate the accuracy of the bounding box predictions. It calculates the precision at a different level of recall by considering different IOU thresholds. The precision recall curve is plotted and the average precision is calculated as the area under this curve. The mean average precision is nothing but the metric that calculates the average precision across multiple object classes. It considers average precision values for each class and provides single summary measures of the performance. Here we can see that we have some mean average precision and trailing loss curves that is been taken directly from the YOLO model. We have seen the results. Now I will hand over to Ashutosh Sahu for further explanation of the CNN models. The one of the CNN model that he will be explaining is U-net model.
Now I will explain about the U-net method that we have used. U-net is a popular CNN model for biomedical segmentation. It is a specific set of symmetric encoder-decoder instructions which is capable of semantic segmentation of images within seconds on a modern GPU. For this, we have used a nuclei dataset available on web. Our goal is to segment the images which contain the images of the cell. The goal is to separate the nucleus from the background of the cell. These are the results that we got from our model. On the left, in the actual image, you can see the blue region corresponds to the nucleus of the cell. In the second image, we have the ground truth image. And on the right side, we can see the segmented image of the actual image. In the segmented image, we can see that it is very close to the ground truth. And these are the performance metrics. Here we can see that the model achieved an accuracy of about 96%. Now, after applying all the four methods, we can conclude the following things: that the CNN-based segmentation are easier to implement than classical methods, and the results are more compelling than traditional methods. Thank you for listening.